Hello everyone, I hope everything's going well with you. Let me introduce myself. I'm Khaing, a lecturer from Myanmar Institute of Information Technology. Now, I'm going to present about rate-adapted peer-to-peer stream margin for hybrid sensor data recovery. This is the outline of my presentation. Firstly, I'd like to give a short summary on background information and major reasons for our research. In Internet of Things IoT data recovery, such as video data recovery or sensor data recovery, stream margin plays an important role to reduce the bandwidth consumption. In the existing peer-to-peer recovery scheme, to maintain the steady nature quality expectation, past data delivery rate adaptability is not considered in stream margin. However, depending on any form of emergency or issue, there are cases in which the loss encounter client accept the quality changes at this recovery time. Hence, we introduce a rate-adapted peer-to-peer stream margin for hybrid sensor data recovery scheme. From our simulation result, we confirm that our proposed method reduces more of the number of recovery streams. Next, let me introduce the problem description of existing peer-to-peer data recovery and how our proposed method solves it. Since IoT devices such as sensor and other smart devices generate valuable streaming data for our daily life, IoT data recovery is important to achieve reliable data analytics and high data availability. In IoT data delivery, recovery occurs when one of the clients encounters data loss and then requests recovery from the server. For different past data requests, the server proposes different recovery streams, resulting in more bandwidth consumption. Since stream margin reduces the number of recovery streams, it is used for data recovery to minimize the total server bandwidth. In hybrid sensor data recovery scheme, peer-to-peer data recovery is allowed in order to reduce the disadvantage of server-oriented recovery, such as load-of-server and scalability problem. Here, the pass data delivery rate is directly proportional to the skip rate of recovery stream. Faster pass data delivery rate means more lost data is skipped in preparing recovery stream to faster catch up with the real-time IoT data stream. As a result, more quality degradation occurs. And the tolerable quality degradation of each peer may vary at its recovery time, depending on several conditions. However, existing peer-to-peer streaming strategy do not consider it for data recovery. Therefore, the aim of this paper is to propose a rate-adapted stream margin method for hybrid sensor data recovery. Currently, peer-to-peer stream margin occurs when the recovery request the client and the existing peer assist and recovery stream request same pass recovery data with same pass data delivery rate. However, there may be peer who can tolerate quality degradation at any recovery time. Therefore, for the rate-adaptable environment, there is stable bandwidth consumption overhead by considering coincident stream margin with same quality expectation. This figure represents our assumed system environment. Only in cases when there is no peer that asks for pass data delivery, server proposes recovery stream, in this way reducing its load. In our Azure system, the server Azure 2 delivers the real-time data with 30 frames per second for past data delivery. The loss data delivery rate of peer may be 60 or 90 frames per second depending on their preferences. Unlike existing peer-to-peer stream margin method, our proposed method considers the past data delivery rate adaptability of each peer. In our proposed method, stream margin occurs in three cases. The first situation for stream margin in our proposed method is same to that of the existing method. In case 1, peer-to-peer stream margin occurs when peer and existing recovery stream requires same past data with same skip rate. In addition, in our proposed method, margin event happens when peer or existing recovery stream requires same past data with different skip rate and requires that peer can tolerate quality degradation. Also, in case 3, stream margin occurs when peer and existing recovery stream requires different past data with different skip rate and requires that peer can tolerate quality degradation. Now, I'd like to give an example of case 2 and case 3 margin scenarios. So let's assume there are two peers, P1 and P2, and recovery stream is delivered with 30 frames per second. The past data delivery rate of P1 and P2 are assumed to be 60 frames per second and 90 frames per second respectively. Here, 60 frames per second past data delivery rate means that the skip rate of the recovery stream is 2. In other words, the recovery stream delivers 30 frames per second, skipping every other frame from 60 frames. And 90 frames per second past data delivery rate means that the skip rate of the recovery stream is 3, resulting in more skip data, more quality degradation, and faster catch-up with the real-time stream. P1 is tolerable more data loss than its defined amount at time default. These figures are for the explanation of case 2 stream margin. In this figure, P1 and P2 encounter data losses at time T1 and T2 respectively. At time T3, P1 starts its recovery and again it encountered data loss at time T4. Between time T4 and T5, P2 starts its recovery. Therefore, at time T5, when P1 starts its recovery, there is an existing recovery stream. Although P1 and existing recovery stream require same past data, they have different skip rate. In the existing stream margin method, different skip rates are not considered for stream margin. Therefore, in figure A, at time D5, there are two recovery streams. However, in our proposed method, at time D5, P1 is added at the residual of the existing recovery stream because P1 can accept the quality of the existing recovery stream. In this way, the number of recovery streams is reduced. In a similar fashion, in this figure, P1 and P2 are assumed to encounter data loss at time T1 and T2 respectively. At time T3, P2 starts its recovery. At time T4, when P1 starts its recovery. Let's assume that the steady recovery data difference of existing recovery stream and P1 is just 1 frame. Since the skip rate difference of P1 from P2 is also 1, it means that P1 is tolerable more data loss at time T4. Therefore, in our proposed method, stream margin happens at time T4. However, in the existing margin method, Since P1 and P2 had different skip rate, the server has to generate two recovery streams. To see the basic performance of our proposed method, simulation is done using the parameter values described in this slide. Throughout the simulation time, each peer is assumed to encounter data loss multiple times. So, Poisson scenario failure recovery patterns are generated for the simulation. This figure is the second trial failure recovery pattern. In this figure, 8 ASICs represent elapsed time, and 1 ASIC shows failures or recovery count of peers. The simulation result is shown in terms of the average number of recovery streams. At the comparison method, we use a 16 peer-to-peer coincidental stream margin method. The merits of our proposed methods can be seen clearly when the average recovery start interval becomes large. It is because when the average recovery start interval is large, the number of peers in failure simultaneously is large, so more probability for stream margin exists. Since our proposed method considers not only coincidental stream margin but also rate adaptable stream margin, our proposed method reduces the number of recovery streams more. In conclusion, our proposed method can faster reduce the number of recovery streams for IoT data recovery in rate-adaptable environments. In the future, we are planning to do more evaluations that are based on different stream margin methods. Thank you very much for watching my presentation.